This meeting
It's
is
not
being
an emulator.
recorded.
So for it to not be an emulator, it has to be a physical typewriter thing punching paper. And the fact that it is not physically punching paper is what makes it emulating, because it is emulating that. And some of the things that is emulating is it actually has to emulate the time of the physical push stamp, because that turns out to be important for a lot of legacy code. And it emulates the monospace width of things by default, because also turns out to be important, because it turned out like back in the day, pressing tab was not like a tab character that got inserted. It was moving the little head that punches paper over for characters. It turned out there were multiple different types of enter keys on a keyboard, one that moves your terminal head back to the beginning without going down, one that goes down without moving back to the beginning, and one that does both of those together. Also ones that go up. Also, it turns out when you press backspace back on an original keyboard, it didn't actually delete things, because you can't delete things from physical paper. It just moved the character, the head where it's going backwards, so that the typist could then press X over it to delete it. And yep. So all of those things that seem weird about like terminal stuff, they all somehow come back to being backwards compatible with that stuff. Yeah, so a lot of people have sat down and said, okay, like there's all this cruft, let's just do something from scratch now at this point and do it right in a proper way. And then nobody ends up using it because it's not backwards compatible.
Something that's like backwards compatible with virtual emulators, but not with physical ones.
But then, like, so the people who are in charge of all of these operating systems and maintaining them are even older and more cranky than I am about things. And so there are actually like physical offices in the US government, especially in the military, where these original like 1940s typewriter systems are still in use. Nuclear, anything in the nuclear system is managed by those physical typewriters to be very survivable in case of attacks on the country. And then there are, all the other layers in between there. There are people in active use of those things. And like the vast majority of casual users like yourself are not using that old fancy technology, but you are also not pumping in hundreds of millions of government tax dollars into maintaining things. And so your opinion counts a lot less than some admiral's opinion sitting in Washington, D.C. somewhere. And it's not just like military stuff. Post office still runs a lot on very old technology like that. My dad's a scientist at he's retired now, but was at the U.S. Geological Survey, measuring groundwater things, making sure it's safe to drink. A lot of the systems that make sure that tap water is safe to drink rely on those like old technologies.
And like all their data outputs in like fixed width format and stuff like that.
Yep. So anybody who has like an interest in aviation, this is the most common place where these weird fixed width format stuff comes up, is anytime there's like anything involving aviation. So like we have two airports pretty close to here. They make pretty regular announcements that go out to, certainly the newspapers here monitor them, but anybody who has to do anything in like the sky remotely also monitors them. So like the construction people going on right now monitor that, and they have to read all this like fixed width stuff because it's all backwards compatible with things. Okay, let's see. So welcome, to our CS 181 and talking about grammar stuff. I'm in the topic 6 folder still, and a handful of announcements for us for today. So the first one is that all grades here up to date. So if you have any issues with your grade, then you should let me know so we can get that fixed. Next one here is this Friday. I'm not going to have the normal office hours because my other class is having a midterm next week, and it'd be good for them to have a review session, and that's the time that works. So I apologize for that, but I'll be focusing on them for this Friday's office hours. Next Friday's office hours, though, I'm going to be forbidding them from coming. So if you want to talk about things, that is a good time to come. And partly because of this, but also partly because of other reasons, the deadline for your homework that we started talking about last time, the arithmetic homework, I'll push back to the end of next week. So not this coming Sunday, but the Sunday after that. So there is still be plenty of office hours time for you to come and talk about that if you would like to. Number 5 here, more important-ish, maybe things, concrete things that you have to do for this class. So by next class, the rubric for your project, that should be finalized, or you should have a good draft of that. My suggestion of how you should submit this is creating a new GitHub issue. So not following a previous one, but a new GitHub issue, one just for you and your project. And in the issue, have a table that contains like your basic rubric, 2 columns, the percent of your grade for whatever that particular task is. Each row is a task. And then column 2 is the name or description of what that task involves. And my recommendation here is that you should be very detailed in doing this, as detailed as you can reasonably be, because this is your contract with me about how to, or how I will be grading you. And so the more detailed you are, then the more we will be on the same page about what to expect, and the less chance there will be for any sort of bad surprise in your grade. If you have a very detailed rubric, a very detailed contract with me, then it's very easy for you to meet that contract, know what you have to do in order to get whatever grade you want, hopefully 100% on the project. And I suggest a GitHub issue here so that it's easy for me to reply and suggest changes, and we can do a little bit of back and forth about what's appropriate for your particular project. And then at some point we will finalize that, and that will be your rubric for the class. This is not a required way of doing this. This is just one suggested way, I think the easiest way to do it. But if you feel that there's a better method for submitting your rubric, whatever method you feel is better, maybe more appropriate for your project, then go ahead and do that. Let me know, and I'll probably say yes. And again, goal is that this should all be finalized by the end of next week so that there's no questions about what you have to do over the next month after that before the end of the course. Any questions on any of the rubric stuff or anything so far?
Is there time for us to talk to you about it next Monday, or should we treat it more like
So this is definitely just a first draft. If you edit it throughout the week, that is fine. It's also fine that if you feel like you really need to talk to me, then you don't have to submit it right away on Monday. There's no hard deadline at all with this rubric stuff. We just don't want to put it off too long so that there's time for you to actually complete the stuff. So yeah, if you really want to meet, which is good, to talk about the rubric beforehand, show me a draft and walk through it in person, then it would be fine to do that either next Tuesday or Friday in office hours. Good question. Any other questions?
I have like a clarifying question.
Sure.
It says like the percent of your grade for the task. That's like percent of like the project.
Percent of the project, yeah. Yep.
Have you decided for sure that we're not doing anything there?
For sure, yes. Decision is that you'll just schedule a time to me to present your project to me, talk to me about it. Probably be a half-hour-ish time slot, and you'll, I don't know, give me whatever your spiel is about the project. Then I will walk through the rubric here, checking off that yes, you did all 7 of these tasks perfectly. You get 100% on the project. Good questions. Any other questions? Okay. One last thing I'll say here is that the whole project portion of this course and other portions of this course, but definitely the project portion of this course is intentionally very vague in a lot of the things that or instructions I'm giving you, or the requirements here, intentionally very vague to help you get some practice with dealing with vague requirements about things, and also to help you get some practice of totally doing things from scratch on your own with as little pushing from me as possible to do this. That's often a skill that is often not developed in CS curriculum. So that's one of the maybe meta goals of this project, help you figure out how to do bigger projects on your own with relatively little guidance. Last announcement thing here, number 6, classes for next semester. The one that I'm teaching next semester that might be interesting to some of you is the big data class, CSCI 143. It is required for the data science major. It counts for CS major, CS sequence, or data science sequence at any of the schools. And the main one sentence summary of it is how to build Instagram. So Instagram, major website, has many petabytes of data. You have to be able to access that data in milliseconds in order to generate a web page and serve it to people. And so we'll be talking about in the class parallel processing on remote servers, how to do that, how to set up, say, an army of 1,000 servers that will serve your data to users. Concrete algorithm that's good to put on resumes is MapReduce. Shell scripting here, do 2 different types of shell scripting, POSIX and Bash. So this is using the terminal. And I guess I don't have Vim here anywhere listed, but also very heavy on the Vim and everything about the terminal inside of here. Git, made you do a handful of things with Git in this class, but you'll be getting into all the gory details of Git in big data. Another tool called Docker, which is related to all of this remote server, parallel processing stuff. And then the main portion of the course, these 2 database systems, Postgres and SQLite, how to write SQL that is correct, does what you want it to do, and how to make it fast. Again, querying, say, terabytes or petabytes or even larger amounts of data in just milliseconds so that you can serve things in real time. So that's my course. And then other courses, if you have questions about what's going on in the math department here or the data science stuff, the math tea, there'll be a math tea here this Thursday. This is tomorrow, Halloween, October 31st, 3:30 to 4:30 p.m. in the Ath courtyard. Math faculty available to ask questions about courses, so that includes me, but everybody else, and then the math club providing snacks for the event. So you're welcome to come to that. Encourage you to come to that. I'll be there. But I guess, nothing else I have to say about that. Any questions about anything administrative before getting into technical things today?
How difficult is it to get into big data?
How difficult is it to get into big data? All of you have a guaranteed spot if you want to get in. Yep. Yeah, and a lot of you have already taken about it. If you want to take it again, I will guarantee you a spot. It won't count for credit, but you can show up. Okay. Anything else? Anybody want to talk about before we get into talking about grammar and coding stuff?
Are there any other math or CS classes
Other fun math and CS classes. I have no idea what else is being offered, actually. I will find out tomorrow as well. So graph algorithms, important one. Anybody who, let's see, so for the data science major here, one of the, it's a new major. Every time you have a new major, there's always some things about the major that are weaker than other things. In our case, one of the things that's weaker about our data science major is the computer science component of data science. And one of the things that is one of the most important classes in a CS major that's not required in the data science major is an algorithms course. A lot of students see our CS46 course or other data structures courses, and it has a name like data structures and algorithms. And so you think that if you take that course, you're also taking something like an algorithms course. But Professor Cannon's course is the algorithms course that's basically the same thing as for a CS major and very different than the data structures and algorithms course. I would describe it for a CS student, it's the #1 most important course in their major. One of the many reasons why it's important is that if you're going to get jobs somewhere, you have to perform a technical interview or do leak codes sort of questions. And this graph algorithm course that Professor Cannons will be offering is like the course that tells you how to solve all leak code questions and pass technical interviews. The big data course here, one thing that's not listed here is that this course is designed to help you with technical interviews related to SQL things. So for data science interviews, SQL technical questions, much more common than leak code style algorithm questions. And this is the course for that. But for more software engineering sort of roles, more traditional computer science roles, the graph algorithms course is the better course. Yeah, so that is an important and good course. Other than that, I have no idea what's being offered. But that's a good question. There's also like no program for the math T. You can just come and go as you please. So there, if only like 5 minutes of it is a time that you're available, then you can just come for those 5 minutes and talk to whoever you want to talk to, ask whatever questions you want, and then leave. Okay. Everyone's ready to start coding technical stuff? Way down here, the bottom of our, oh dear, what did I press? Bottom of our README file here. I have put up the last part of the homework. So yeah, a lot of stuff going on in this topic 6 folder here, 3 different homeworks. I put up this part 2 about implementing your own esoteric language, ESOLang. We may or may not start talking about that today, but we will definitely finish up all the things that we need to talk about the arithmetic assignment today. And again, the arithmetic assignment originally due this coming Sunday. I still recommend that you get it done this coming Sunday. There's no new material that you'll need next week to be able to do that, but I've also extended the deadline just in case you would like to have a extended deadline there. This ESOLang assignment, I do not intend to extend this deadline. So it'll be two assignments due the November 10th. Okay, so last time, so I've switched my screen over here to these side-by-side terminals. They're both in my topic 6 grammar folder here. And last time we were looking at the example2.py file as a sample of the things that you'll have to do for your arithmetic homework assignment. That again, there's a grammar up here, defines this context-free grammar and interesting things about it that you'll have to either modify or apply in your homework assignment. And then there are 2 ways of interpreting this grammar. This interpreter right here and this simplifier down here. And I've called this a simplifier because it's really simplifying in this particular application. What it's doing is simplifying this number, this mathematical expression, down into an individual number. But this simplifier is an instance of this transformer class, and the transformer class is more general than just being able to simplify things. In general, it transforms these abstract syntax trees or parse trees from one language into another language. One of the key things to be taking away so far is that there is this clear distinction here between grammar and semantics, or syntax and semantics. That the code up here defines the grammar of whatever language we are working with, and it doesn't define what this grammar means. It just defines that there are these things like pluses and minuses and stars and slashes, and they can be arranged in certain ways as defined by this grammar, but there's no semantics associated with this grammar. There's no meaning that this star right here has to actually be multiplication the way we normally think about multiplication. The meaning behind this grammar comes from these classes down here, this interpreter class and this simplifier or transformer class. And this is an important distinction between syntax and semantics, or grammar and semantics, a distinction that we will revisit many times over the next week or two as we're talking about this grammar concept here. And again, right now we're talking about it in the very formal context of machine languages. We will extend this probably in about 2 weeks, not next week, the week after that, to talking about natural languages, that this is all like one of the reasons for talking about formal languages here is that it is a simple example of natural languages, that programming languages, despite being hard to work with in many ways, they are also much easier to work with in many ways than natural languages. So there are maybe, I don't know, it's maybe a little bit confusing at this point how all this stuff connects to the language model stuff that we've been talking about. At this point, the only real connection that we have is inside of something like whisper.cpp or llama.cpp. You can define a grammar, something like this, slightly different syntax, but the key idea is the same. You can define a grammar like this, and llama.cpp or whisper.cpp will restrict the output of the model to stay within this grammar. And so in this case, if we wanted, say, to have a calculator that you could talk to instead of just typing to, then we could use whisper.cpp with a grammar something like this to enforce that all of the things that the user is saying are mathematical, valid mathematical expressions somehow. As a big picture overview of things that we talked about so far, any questions at a big picture level? Okay. Let's see. One of my hobbies, since we're talking about language in this class and grammar in particular right here, semantics in particular here, one of my hobbies is thinking about the origin of words and phrases. And so one particular relevant phrase right now is nonplussed, that this has two meanings. The original meaning is that coming from the Latin of non and plus, plus meaning to add something, and non meaning you can't do it, that somebody is nonplussed if they have nothing to add to a conversation. But the original, so that's the original meaning right here, nothing to add. Nothing to add. And then Americans, this was the meaning in English for like 500 years until like 50 years ago when Americans decided that that wasn't good enough. And nonplussed now also means that you're so confused that you have nothing to say. And so you all definitely seem nonplussed to me right now, but I'm curious about which one of these two nonplussed versions you all are. Does it feel like the things that we're going through so far are mostly straightforward, and so it's so simple there's nothing to say about it? Or is it so confusing there's nothing to say about it?
I'd say one.
Number one? Okay. Yeah, so the code here, like all of this code is super simple and straightforward once you get it working and you're able to look at it. Like, so if we take a look at line 78 right here, this is defining the semantics of our add rule. Again, this add rule, the name of our functions, the name of our methods in these transformer classes or simplifier classes, what did you do there? The name of any of these methods, they correspond into the grammar. The rules over here, these synonyms, or yeah, synonyms is a good word here. This is a synonym right here. Mul is a synonym for this expression right here. And these synonyms correspond to our methods down below. And I'm just now realizing there's a pretty serious typo here where I have mul as a synonym. I had previously mul right here as a synonym for subtraction and also mul as a synonym for multiplication. That would be a bad thing to do, and that should have subtraction or something like this as a synonym for subtraction. And so the code that is written and working should all be very, very simple and look very simple. And if you have functions that look very complicated and scary, then you've gone down the wrong track somehow. So in some sense, this is all very simple. But in another sense, this is all can be very, very complicated and difficult to write because, well, for many reasons. But one is that the error messages that you get with this kind of code the error messages are very, very long and confusing. So here I have one expression up here. Let's go ahead and use my doc tests, Python 3-m doc test example 2, just verify that that is in fact working, and we don't get any output right here, so that does verify this is in fact working. But if I were to modify this function right here so that we had some sort of error going on, like I forgot to subscript the 1 right there and I said children of 0 plus children, then we're going to get some super scary looking error message here that's like 3 pages long. I have to press the page up button 3 times to even see the whole error message. And this int and list, unsupported operand types, that's, in this case, because I modified this, it's easy to see why it's saying that this children right here was a list, and this thing over here after subscripting, the square brackets here called subscripting. After doing that, we get an integer out of it, but not always obvious how these error messages correspond to what the mistakes are up here. So it's very easy to go back and forth between these two sort of feelings of nonpleasantness and think that things are very simple, because in some sense they are simple, they look simple, but then also if things aren't working, they're so confusing, you don't even know where to get started. Let's see, does anybody have anything that, before we go on and talk about anything new, anything that you feel like it would be helpful for us to talk about, review from last time? Yeah.
Could you explain the difference between the interpreter and the simplifier?
Yeah, this is a really good question. So at this point, the interpreter and the simplifier can do all of the same things. They have the same amount of power. And so you're really implementing the same thing twice with the simplifier and the interpreter. What we will eventually see, though, is that the simplifier, or in particular the base class here, the transformer is much more limited than the interpreter. Lark.transformer is more limited than lark.visitors.interpreter. It's a little bit awkward that in the Lark library, transformer here is a class directly inside of Lark, and interpreter is a class inside of lark.visitors, because they are very closely related to each other. Mathematicians would call these two things duals of each other. And the reason they are dual to each other or somehow opposites of each other is that the transformer interprets the tree, or processes the tree, or walks the tree, or uses the tree. A lot of different verbs that can work right here for the transformer, but the transformer interprets the tree bottom to top, from the leaves to the root. That has several implications for us. One of them is that you don't have to manually managing recursion. So down here in our simplifier class, which is again based off of this transformer class, in our simplifier class down here, we're not talking about recursion anywhere. There are no function calls anywhere inside of any of these methods. All we are doing is taking the children and somehow applying them to each other using the semantics of whatever that particular grammar rule is. And the reason this is working from the roots to the root node, sorry, from the leaves to the root node, is because the multiplication right here, this is assuming that our leftmost child and our rightmost child, children 0 and children 1, have already been processed somehow. And in this case, the number would be for this particular grammar, number is the leaf node at every point. And so we're converting it from the node into an actual integer so that when we get to multiplication or addition or whatever the current rule is, we have integers in our children that we can work with, process, and then the current multiplication node will get replaced by whatever this result is. So we're somehow simplifying the tree, going from the leaves to the root. No manually managing recursion. Another property here of the transformer is that the amount of computation is very limited. That you're guaranteed to visit every node in the tree exactly once. The interpreter class is the opposite of both of these two things. So interpreter interprets, same verb for both of them, the tree from root to leaf. This means that you must manually manage the recursion. And depending on how you manage that recursion, you can actually do a lot of extra computation. Depending on how you manage that recursion, you can do a lot of extra computation. We'll see exactly what that means when we talk about the SOLang homework. For the arithmetic here, there is no extra computation that can happen. But what we will see is that if you have more complicated grammar rules, things like for loops or functions or if statements, the interpreter is able to work with that, but the transformer is not able to work with that. So able to compute, we'll call it all control flow, like if statements, for loops, and function calls. So the interpreter is strictly more powerful than the transformer. Interpreter, strictly more powerful. And what I mean by that is that anything a transformer can do, an interpreter can also do. A lot of beginning junior programmers, and by that I mean people who even have, say, like 5 to 10 years of industry experience, so much more senior than you all, but still also including you all. A lot of these junior developers have a sense that using more powerful tools is always better. But one of the things that defines a senior developer, makes somebody a senior developer, is understanding what the right level of power for a particular tool is, or what for a particular project, a thing that you're trying to accomplish, how powerful of a tool should you use? So one of the defining characteristics of a senior developer, or I will even just say a good developer, is understanding and using the right level of power for a task. And in particularly, like explicitly limiting your power. Explicitly limiting your power is sometimes good. But if you're using a language that is too powerful, you can accidentally insert different types of bugs. It makes things hard to reason about. But if you're purposefully limiting your power, then you can guarantee that you don't do certain types of accidental bugs. And so one of the things that we are going to see is that these transformers are very useful for translation tasks. Your first homework assignment here with arithmetic has you implement a concrete machine translation task between two different arithmetic languages. And transformers are very good to that because we can guarantee that we don't accidentally do too much computation and do more than just translate, but actually do computing. Okay, so this is probably more of a detailed answer than you were really hoping for, Amelia. The actual, like, the thing that's important to know at this point about the difference between this transformer and the interpreter is that the transformer, very simple implementations, no managing of recursion. The interpreter class up here, all of the implementations will be a little bit more complicated because you have to explicitly manage the recursion. This self.visit over here does the recursion, says go into the left child right here, do whatever processing you need to do on this left child to compute that child, to get the semantic meaning of that child, and then store that result here. And then the very last thing down here, this is the same as what the actual implementation in the transformer is of add. That the transformer only has this line, but the interpreter also has these two lines up here that are managing the recursion for us. Did that answer your question? Okay, let's see, let's do one more thing here since we're talking about the interpreters. Let's go on and see how to just remind ourselves how to implement one of these rules with the interpreter and talk about the multiplication right here, the star. I'll come down here and well, let's see, actually first, anytime I am working on a project, I always start by defining my test cases about how will I know when my task is complete. And so let's go ahead and define some test cases up here for our interpreter. This is the format that your test cases are in for the homework, where at the very beginning, I define the very first test case defines this interpreter instance of the big I interpreter class. There's a common syntactic pattern in Python where the class names are uppercase and the instances of those classes are lowercase. There's nothing in Python that forces that convention, but it is a common convention. And then down here, I can do interpreter.visit of parser.parse of some number, and it should output that actual number. That the parser.parse here again generates the abstract syntax tree. This should be a very simple syntax tree. And then the interpreter.visit will process that syntax tree, converting it into a number. Let's verify that this does in fact work. I verified that by running my doc test down here and seeing that I got no output. One good thing to do is always just to, anytime I'm adding a test case, just to make sure that I'm not doing something totally weird like running this on the wrong file, actually purposely cause this test case to fail. So I've changed this, like I should not get 124 from this code right here of 123. And I do that and I do get a failure here. So I know that I am in fact running the right code and everything, and that my interpreter does work for 123. I have the add function, add method down here. So that probably means that the add stuff is working. So 123 plus 4 should get me 127. Let's check that. And it does in fact get me 127. I know that because I'm not getting any output down here from my doc tests. And so that gives me good evidence that my add down here is working. So let's go on to the multiplication next. 5, 6, GG, take me to line 56, F plus, take me to the plus, R star, replace that plus with a multiplication. And let's see, that's more complicated than the math I want to do in my head. So let's change that to 3 times 4 now and change this to 12 down here. To that we will know that multiplication is working if we get a 12 down here. Run that, and we get an error message down here because we have not implemented the multiplication function yet. In order to do that, come down here, def mul self comma tree like this, and there are 2. Let's see, for a simple function like this, I can probably just write out the code exactly what it should be, because I already have the addition up here. The semantics of multiplication and addition are very, very similar. The only difference is changing the operator here from a plus to a times. So I can probably be pretty confident by just copying and pasting this code right here to get the multiplication, that the multiplication will work. We also talked, though, about one good debugging technique is you can enter into an interactive Python environment at any time in your code by adding this line right here. Code is a built-in module into Python that supports like manipulating the code as it's being run somehow. And this interact function right here allows you to get directly into a Python shell and have access to, say, this tree variable to manually inspect it and to see what are, for example, the arguments to the mul function here. What do they actually look like in practice? If you use code like this inside of DocTest, this will happen where now I'm in my interactive console right here. But unfortunately, Python does not allow you to type things in. One of the things that DocTest does is it disables something called standard in, which is how you actually type things in. So you can't use this debugging technique. This is incompatible with running in DocTests. Incompatible with DocTests. And the way to use this now would be to actually open up my file in, we'll do interactive mode, Python 3-i, example2.py like this. I'm in interactive mode. This is interactive mode, not at this line right here because I haven't run this line yet. This is the interactive mode just after having all of this code in this file loaded into the Python interpreter. And I have access, for example, to this tree variable right here and the tree1 variable right here, tree defined. Let's see, I can do /tree to search for it. Here, defined on line 38 right here, 123 plus 4. And then /tree1, defined right here as running the interpreter on that tree. Tree1 actually giving me the number right here. If I do, say, AST equals parser.parse, but now I add the, instead of 123 plus 4, I change this to what my doc test is, testing the multiplication 3 times for it like this. Then I generate the abstract syntax tree, which contains the multiplication in it. Notice that I did not run this code yet because this is not the grammar code. This code is not in the grammar portion, not in the syntax portion of my file here. It is in the semantic portion of my file. And so that will only get run when I do this actual interpreter.visit line. So I do interpreter.visit here, now AST, and I'm now at this point in my code. I know I'm at this point in my code because you can see all of this Python information about being in a new interactive console has displayed out here. And I now have access to this tree variable right here inside of this function. It's like I'm currently on line 70 right here in the Python code, and what can we do with that? And we can have this tree right here, and we can see that it has a 3 and a 4 as parameters with those are our numbers as their nodes, and multiplication is the thing that's joining them together. There was also this tree.pretty, a useful debugging technique that converts this ugly thing right here that's hard to read into a prettier thing in order to actually display it nicely. So pretty generates the string, and then if we do a print tree.pretty, it will print the tree in a nice way. And so I can see there are 2 leaf nodes here, both with their type, their name being number, value of 3 and 4, multiplied together with this mul operation. And now I can understand, okay, since I'm at a mul right here, the left thing right here is my leftmost argument, the right thing over here is my rightmost argument. And so doing something like v0 equals self.visit, I always need to recursively call on my children when I'm inside the interpreter because I need to interpret this subtree right here. I need to not just multiply this tree times another tree. It doesn't make sense to multiply trees together. I need to evaluate this tree right here to convert it down into a 3. So that's what the self.visit will do, is it will evaluate the tree, interpret the tree to get me the actual concrete number. The 0 is the leftmost child, and the 1 is the rightmost child, and then return v0 times v1 like that. And now on the left-hand window over here, I have 2 nested interactive console sessions running. I'll press Control D once. You can see it now says now exiting interactive console. This was the interactive console that was inside of this right here with this tree. If I type out the tree variable now, I get a different tree than I had before because I'm now in an entirely different console session. Different tree contains 123 and 4 with an add operation between them. And Control D again takes me out of Python entirely. I now go back to my doc test, verify that things are working. I'm going into the interactive console again because I forgot to comment out that line. Let's comment out that line, come back over here. Control C, Control D, up arrow. run it. There we go. And so the multiplication here is in fact working, and and I know that because the doc tests are passing. So for your homework, you'll have to implement a handful of things again, both in the simplifier and in the interpreter of all of these operations. You'll have to add some things to the grammar, and when you add some things to the grammar, also change how the add more things to the interpreter and the simplifier down there. I said a lot of things without stopping for breath there. Any questions? Okay. Should we, let's see, we have two options at this point. I could do more examples from the first arithmetic homework, or I could go on to new stuff that's maybe more interesting, if you all feel up for that. New stuff? Okay. I like it. Very, you know what you want. Okay, so here in the SLang folder right here, this is going to be your new homework right here, and let's talk about what's going on inside of here. There are 4 different important files inside of here. I call them level 0, level 1, level 2, and level 3. Each one of these files is adding new features to an esoteric language that you will be implementing. And a lot of the features are already implemented, but you will have to add new features. So as an example, for loops are currently implemented, but they have certain restrictions. You'll have to remove those restrictions from the for loops, and you will have to implement while loops. You will have to implement if statements, and you will have to implement function recursion in this language. So let's talk about how all of that works. First thing here, this double underscore main, dunder main function. Let's see, where am I? Grammar, let's go into the SLang folder. Anytime you have a file that's double underscore main, the way that you use it, Python 3-m SLang. Here, I'm in the SLang folder, this SLang folder right here. This and Python folders and modules are the same thing. So this -m here means run the module that is called SLang, which means go inside the SLang folder and look for this double underscore main.py. And if you do that, then you will get into this prompt that looks like SLang like this and allows you to type in expressions that are inside of our new esoteric language. And all of the stuff here in level 0 arithmetic is the same stuff from your first homework assignment, all of the arithmetic stuff that we were just talking about. But there are also these other features about the language now, adding the fact that you can do more than one statement at a time or create variables, something like a equals 3 and then a plus 4 to do 7 here, keeping track of what the a variable here is equal to. Or doing things like b equals 7 and then a semicolon to chain this together to c equals 8 and another semicolon to say what is b plus 7 or b plus c, and that gives us 15 down here. So that's what this level 1 statements is implementing, is adding variables to our language and allowing us to chain commands together with this semicolon to put them all in one line. Level 2 over here, the loops, we can now do something also like for I in range 10. The syntax here in this SLang is that the body of the for loop will be inside of curly braces like this. We can say something like a equals a plus 1, like that. And then what is a? Its value is 13 after adding 1 to it 10 times. So level 2, like this, implements loops, and then level 3 implements functions. There are 2 built-in functions. One is a simple print statement, print 34, gives you the number 34, and the other is a function called stack, which displays all of the variables that are currently in scope at this point in the code. Those variables in scope called the stack of your program. And yeah, so that's what all of these Python files here are doing, this level 0, 1, 2, 3, and 4. I've divided them up into 4 separate files like this for 2 reasons. One is that it's just generally good practice. There's a common thing to do when writing programming languages is to have the code that's about a certain feature of the language grouped together. But another is because in the main function over here, we're allowed to limit what sort of syntax our programming language has access to it. There is this level parameter that we can pass in, -- level. And if I say level equals 0, then my esoteric language only supports arithmetic operations and does not support something like variables. We get a syntax error now when I am only at this level arithmetic 0. But if I leave this, so Control D to leave, up arrow, change my level to 1 over here. Now I still have arithmetic, but I also have variables, but I do not have for loops for I in range 10, a equals a plus 1. That gives me an error message. So one of the purposes, several purposes of this assignment, one of them is to get you a sense of how programming languages are implemented. It'll help you as a Python programmer or whatever kind of programmer you end up being in the future to understand under the hood what the Python executable is doing. Another is to get a sense of like how much power do you get from different types of features in a programming language so that you can see that certain things you will be able to implement at, say, this level, but not at this level. Certain things implement at this level, but not at this level, and so forth. It will turn out that transformers, so like ChatGPT sort of stuff, can implement everything in the arithmetic and statements, and currently everything that's inside of the loops right here, but not they don't have the power of this functions level. After you add while loops into the loops over here, then the transformers, ChatGPT, they will have the power of for loops, but not the power of while loops. So you'll be able to adjust your program over to here to have different power to control the power level that you're using as you're writing code. Okay, let's take a look now at the implementations of some of these files over here. On the right-hand side, I'll open up SLang star.py-p like this. Opens up all 5 of those files at once in different tabs inside my Vim window. The arithmetic.py is the same as the arithmetic homework assignment again, just the base assignment, the part that I gave you without any of the additional features like exponentiation. You're not going to be required to add those additional features here, although you're welcome to if you would like to. The next level here is statements. There is a lot of test code here at the top, doc tests, illustrating what the features of this level are, that you now have semicolons that can separate things. There's curly braces to create code blocks. And the grammar down here for statements looks something like this. There's a few new features of the grammar code here that we should go over so that when you're writing your own extensions to this, you'll be able to understand what's going on. The first here is that notice that my grammar is not defined entirely in a single string right here. Instead, it is concatenating 2 strings together. The first string over here, this level 0 arithmetic.grammar, is being added to my new features over here. So my actual grammar itself is a lot longer than this. This grammar right here does not contain, for example, what the semantics or the syntax rather of the plus operator or the parentheses or any of the arithmetic expressions, but we're getting that from this variable right here. In order to be able to redefine this start rule, there's this %extend feature inside of Lark that allows you to extend what the original start rule allows us to do. So in arithmetic, the start rule the only thing that you can do is you can go to the sum, which inside of it has products or parentheses or numbers. But now we can also, inside of our start rule, have one start rule or many others separated by semicolons. Or we can do an assignment to a variable, or we can do a block. A block is these curly braces right here for, say, the inside of a for loop. And there's also a new terminal. So there are now 2 types of terminal, not just numbers, but also names that, say, a variable could be a name down here. And the atom has also been extended so that an atom can be a number or a name. It doesn't have to be just a number anymore. So this defines the new grammar over here. There is new interpreter rules down here, and I've already given you a lot of interpreter rules down here. These rules are doing the, defining the semantics of everything that is going on. And it turns out that for handling variables, there's no way to handle variables with this transformer style of interpreting a grammar. You have to have an interpreter. You have to go from the root of the node to the leaves of the node in order to handle variables. So the arithmetic that has both an interpreter and a transformer, the statements over here and all of the other ones only have an interpreter without having any of the other features. Similarly, loops over here, each one of these files defines a new extension to the grammar and then defines a new interpreter to interpret that extension. It has a handful of test cases down here that are things that you'll have to, or things that are currently implemented, features that you are able to use. And let's see, the last one over here, function calls. You're able to define functions or call functions. And this interpreter class implements how to do that. What you're going to be required to do for this homework, and we will start talking about in a second and then finish talking about next week, is that you are going to have to add support for, again, the if statement, the while statement, and the for loop in this language. And you will have to demonstrate that your new language has all that functionality by creating examples in the README file and creating your own doc tests that demonstrate that new functionality. Any questions about big picture things before we get into details? Yeah, Ron.
When we're making examples on the README, should we also make like GitHub Actions workflow to like test those specifically? Or?
Yeah, so there is already a GitHub Actions workflow, and the doc tests will be tested with with that workflow. There's not an easy way. This is one of the frustrating things about Python. There's not an easy way to make to test the examples inside of the README file. But the examples in the README file should basically just be the doc tests that you add. So they are being machine checked at some point, but they're being exposed more directly to somebody who's looking at the README file right here. Good question. Other questions? Okay. I can feel everybody's excitement just oozing out of you all. Okay, so let's talk about how to implement if statements here. So I'm going to just work through some of the things that you'll have to do here, and this will get you started on all of that code. There's a lot of choices that you have here. So again, this second version of the project, much more free-form than the first version of the project, where you are going to have not, again, specific test cases that you have to pass, not specific instructions on where to do things. You just have to decide for yourself. But if we are going to have an if statement, we have to decide a syntax for the if statement, and we have to decide where we're going to define that syntax. And again, the syntax always defined in one of these grammar locations. I will choose, I'm feeling like putting it inside of the statements right here, because if statements feel more like a variable related thing to me than they feel like an arithmetic related thing. But there's no, I don't know, real concrete logic about that. To add this, I'll add a new rule to my start rule over here. The start is like any one individual statement is going to be one of these start rules. Basically, like any line in a programming language, any line in Python or another language, that's one of these start rules. Here, this empty rule right here, I want to make sure that I keep that around because that is important, that it allows us to say, have empty statements in our language, which is a useful thing to do sometimes. So I'll add it down here, create a new statement like the if statement like that. And then down here, I'll say what my if statement should look like. If statement, and I'll define the syntax. I'll have an if like this, then it'll have some sort of condition. And then let's see, how do I want to do this? I will use a syntax actually that probably you all have not seen before, but it is very common. It's called the ternary operator, the question mark here. We'll do the condition on the left-hand side of the ternary operator, and then the true statement here, which will be a start, and then a colon, and then another start. The semantics of this if statement. The semantics, so again, this is not something that we define inside of the grammar, but it's sometimes commented inside of the grammar so that we know like why we have the grammar defined the way that it is. But the semantics here is that the condition will, the first start will be run if condition is true, and the second start if condition is false. So this gives us the same power as Python if statements, just the formatting is done a little bit differently. Again, this version is sometimes called the ternary operator, ternary because it has three options down here. Condition, start, and start, three different options down here about what are the parameters to this operator. And it's called the ternary operator and not just a ternary operator because it is the only one that's really in common use. C-derived languages use this notation. And Python, there's been some explicit proposals to add this to Python, been proposals to add it. But Guido killed those proposals. Guido killed them. Python does have actually a similar syntax right now where it only supports, where it's called the inline if syntax. Python supports inline if statements, which are similar to this, but not using these particular operators right here. Okay, there's a lot of words that I said right here just to define that we're having this new kind of condition right here. In order to talk about conditionals, I need to somehow have like Boolean things to know like what is the meaning of true and false. But currently the arithmetic code only supports integers, and I need to somehow think about how do I want to represent true and false in my programming language. In order to make this just a little bit different than Python, we will not do any special Boolean variable type. We will not implement a Boolean variable type, and we will just have our conditionals be represented as numbers. Conditionals represented as numbers, where there's different ways to do this, but I will use a way that is different from Python, where 0 is true and all non-zero is false. This is again the semantics of the C language, and the Unix terminal follow this pattern. But Python has the opposite pattern of 0 is considered falsy in Python, and all non-zero values considered truthy in Python. Because there's no special Boolean type here, my condition over here is going to just be, I can use any sort of expression that I want. I will, for simplicity, start with condition colon number like this. But then we will maybe change this up in a little bit. Condition colon number. Okay, so this is a new grammar for us. We've modified the grammar, and after we modify the grammar, it's important to make sure the grammar behaves the way that I expect it to, that these if statements are going to behave the way that I expect it to, that I don't get weird grammar error messages before I start defining the syntax of this grammar, or before I start defining the semantics that corresponds to this syntax. So on the left-hand side over here, I'm going to press Control-D to get out of my SOLang environment. And now I'll use Python 3. We'll go into interactive mode on my on here on the SOLang / we are in level 1 statements.py like this. And module not found error, no module named SOLang. We've seen this before. The problem is that in Python, in order to import a library, G up to the top, go to my import statements. In order to import this library right here, by default, Python only looks at the globally installed packages for this root level module right here. And so it doesn't know where to look for this level 0 arithmetic. In order to tell it where to look, I need to add the Python path equals dot like this. And now I should be able to load that. Yes, no error messages. That's excellent. And now I can try to parse a string that contains my new if statement syntax. So parser.parse of, we'll do 3 question 2 colon 1. And there is no error message here that this does in fact generate a tree. The tree looks like this. We can call the tree, assign it to a variable, and print it out so that we can see if that tree looks reasonable. Tree dot pretty like this. And so now I get my startup here, if statement, here's the condition right here, and then start going to number like this, 2, start number of 1 like this. So I could maybe clean this grammar up or clean up this resulting syntax tree a little bit if I wanted to by taking out these start nodes here that aren't maybe strictly necessary. But this does look like it's at least capturing the main ideas of what I want here. And so I can go on and start thinking about the implementation and the semantics of this. Maybe before I start talking about semantics, one last test I'll see what happens if I start adding some like computation inside of one of these conditions. If I do the 2 plus 1 over here, my hope is that this 2 plus 1 would all get grouped together as like the true statement, and this 1 over here would all get grouped together by itself. And if I do that, print that tree, then that is what in fact is happening, that the add down here, this 2 plus 1 is contained inside of the true condition over here, the very first of the start arguments to the if statement, and the second one down here is the second parameter. So this means that my if statements, they can in fact have complicated and arbitrary computations inside of them. And well, let's see. Looks like we're having some problems there with stuff to the left. So right now, I can only have numbers. Oh yes, I can only have numbers to the left of the question mark over here. And that's because right now my condition over here, down here, condition is restricted to only be a number. We could, instead of restricting ourselves to be a number though, have ourselves be any possible expression like start over here. And now left-hand side, Control D, up arrow, re-enter, define our tree now like this. It still works, print that. So this is the same tree I had before, but now there's this inside of condition, go down to start right here. And if I change this, so instead of 3, we can now add the 3 plus 2 times 6. I think that's something like that. No errors. And inside of the condition, I can have complex formulas inside of the condition. And these things down here. Let's see, we can talk about, so the next thing to do here is to talk about actually doing the semantics of this, implementing the semantics. What does that look like? But any questions on the grammar stuff? Okay. The semantic stuff probably take us more than 3.5 minutes. So this is probably a good spot for us to stop then. And next time in class, we will go over how to implement this, the semantics of this if statement, and that should get you everything you need for starting on this homework and doing the other things like adding the while loops and fixing the for loops and getting recursion working. So if people have any questions about anything, I'll stick around and get those answered. Otherwise, we will be done for today.